plus a square. This force will have component along x-axis and y-axis as Fx1 and Fy1. Similarly, we have the components of force due to opposite small section as Fx2 and Fy2. When we add the components over all regions of the ring, the components along y-axis will cancel out each other, but the components along x-axis will be added up and the resultant force will be along the line joining the point to the center.
Today, Newton's law of gravitation is used to determine the orbits that take spacecrafts from the Earth to various destinations within our solar system and beyond. In addition, the law allows us to calculate with pinpoint accuracy the time of solar eclipses and other astronomical events in the distant past and remote future. Newton was also able to prove that Kepler's second law, according to which all planets sweeping out equal areas in equal time intervals, as a logical consequence of his law of gravitation. Newton's version of the proof is rather complicated, but the proof becomes simple once you understand the concept of angular momentum, which will be covered later. So, we will show its proof during our discussion of angular momentum. Newton did not know the mass of the Earth as well as the numerical value for the constant g. But if g could be measured, it was possible for the first time ever to determine the mass of the Earth. The only way to measure g is to measure the gravitational force between two objects of known masses, but that's an exceedingly difficult task because the force between any two objects of ordinary size is extremely small. In 1798, an English physicist, Henry Cavendish, was the first to determine it experimentally. Since Cavendish's experiment, the measurement of g has been refined and the currently accepted value of g is equal to 6.67 into 10 to the power minus 11 Newton meters square per kilogram square. However, knowing g not only allowed the determination of the Earth's mass but also those of the Sun and the other planets. With the help of Newton's law of gravitation, can you prove the Kepler's third law of planetary motion? We know that when a planet moving around the Sun in elliptical orbit, let us consider it as circular, because in most of the cases it is very close to the circle. Let the mass of the Sun be ms, mass of the planet be small m, the separation between the two be r, and let the planet revolve around the Sun in time t. According to Newton's law of gravitation, force of attraction is g into ms into m upon r square. This gravitational force acts as centripetal force, which is mv square upon r, where v is the orbital velocity of the planet. We know that the orbital velocity v is equal to 2 pi r upon t. Hence, centripetal force becomes 4 pi square into mr upon t square. On comparing the two forces, we get g into ms into m upon r square equal to 4 pi square into m r upon t square, or t square is equal to 4 pi square upon ms g into r cube. Since g, pi and ms are constant, hence t square is proportional to r cube, which is the Kepler's third law. From this calculation, can you find out the value of universal gravitational constant G? Since centripetal force is provided by gravitational force of attraction, therefore, G into ms into m upon r square equal to 4 pi square into m r upon t square. By rearranging the relation, we get G equal to 4 pi square into r cube upon ms into t square. By substituting the values of mass of the sun ms, orbital period of the planet t and its distance from the sun r, we can measure the value of G. Let us consider this example. Mass of the sun is 1.99 into 10 to the power 30 kilogram. Mean sun-earth distance is 1.496 into 10 to the power 8 kilometer or 1.496 into 10 to the power 11 meter. And the orbital period of the earth is 365.25 days or 3.16 into 10 to the power 7 seconds. This gives G equal to 4 into square of 3.14 into the cube of 1.496 into 10 to the power 11 upon 1.99 into 10 to the power 30 upon square of 3.16 into 10 to the power 7, which is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. I hope you are well versed with the concept of gravitation and different laws governing the movements in the universe. Let us summarize today's topic. According to Kepler's laws of orbits, all planets move in elliptical orbits with the sun situated at one of the foci of the ellipse. According to Kepler's law of areas, the line that joins any planet to the sun sweeps equal areas in equal intervals of time. Finally, according to Kepler's law of periods, the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. In 1686, Newton formulated his well-known law, that is, law of gravitation, which is also known as the universal law of gravitation. According to Newton, every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In other words, the force of gravitation is equal to G times the product of the two masses upon the square of the distance between them, where G is the universal gravitational constant. And currently accepted value of G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. ਹੁਣ ਇਹਨਾਂ ਦੇ ਜਵਾਬ ਦਿਓ। ਪਹਿਲਾ ਸਵਾਲ ਹੈ, define Kepler's law of areas. ਇਸ ਦਾ ਉੱਤਰ ਹੈ, according to Kepler's law of areas, line that joins any planet to the sun sweeps equal areas in equal intervals of time. ਦੂਜਾ ਸਵਾਲ ਹੈ, what is the nature of gravitational force? ਇਸ ਦਾ ਉੱਤਰ, it is an attractive force. So now, we come to the end of today's topic. I am confident that you have all understood the topic well. Thank you for your attention and see you next time again.